It's probably the largest, most complex machine ever built by humans. A silent giant that stretches across entire continents, powering literally everything in our lives. And yet, we almost never see it or even think about it. So today, let's pull back the curtain. We're going to make this invisible system visible and explore the absolute wonders of the electrical grid.
I mean, really think about it for a second. You walk into a room, you flip a switch, and bam, light. Instantly. But have you ever stopped to wonder about the incredible journey that energy took to get to you? What kind of mind-bogglingly complex problems had to be solved in that exact split second for your light to turn on? Well, that's exactly what we're going to break down.
Okay, so the first and maybe the most fundamental challenge is this. Electricity is not like water in a reservoir. You can't just generate a whole bunch of it and store it in a giant tank for later. Nope. It has to be generated at the precise moment it's being used.
And when I say balance, I don't mean it's an approximation. It has to be perfect, down to the watt. Every single time someone, somewhere, turns on a TV or starts a factory machine or just plugs in their phone, a power plant has to ramp up its generation instantly to match that new demand. It's a constant tightrope walk. You see too much power, and you can literally fry the system. Too little, you get blackouts. It is a perfect, non-stop, real-time balancing act.
So how on earth does the grid pull this off? Well, the brain behind the whole operation is something called unit commitment. Think of it as this massive, continuous, super complex calculation. It's constantly looking at demand forecasts, fuel costs, and how efficient each power plant is to decide which station is the cheapest and best one to fire up to meet the next megawatt of demand. It's like an invisible hand, scheduling power across the entire nation second by second. Okay, so problem number one is solved. Supply and demand are perfectly matched. Great. Now for the second great challenge. How do you get that power from a plant that might be hundreds of miles away all the way to your home? You need a special kind of energy superhighway. And the backbone of that superhighway, it's not just some ordinary wire you'd find at the hardware store. It's a specialized piece of gear called ACSR. That stands for Aluminum Conductor Steel Reinforced. And trust me, this thing is a brilliant piece of engineering designed for a truly monumental task. So why ACSR? Well, it's the perfect material for the job. It's got a core of super strong steel, which is then wrapped in lightweight aluminum, which is a great conductor. That steel core gives it incredible strength. That means you can have much longer spans between the giant transmission towers. And longer spans mean you need fewer towers overall, and that saves a massive amount of money. And, just as importantly, reduces the number of places where something could go wrong. But of course, physics always has another trick up its sleeve. When you're moving this much alternating current, you run into a really strange problem called the skin effect. Basically, the electricity doesn't use the whole wire. It tends to crowd onto the outer surface or the skin of the cable. Just imagine a brand new 10-lane highway, where for some reason all the cars decide to cram into the outermost lane, causing a massive traffic jam while the other 9 lanes are totally empty. That's the skin effect. So, how do you fix a problem like that? Well, engineers came up with a really elegant solution: bundled conductors. Instead of trying to use one single gigantic wire, they use several smaller wires bundled together in a group. This massively increases the total available surface area, the skin, for all that current to flow on. It's the electrical equivalent of adding more lanes to that congested highway, which lets all that energy flow freely and efficiently. Pretty clever, right? Now, you have to remember, a system this huge and complex is constantly under attack. We're talking storms, falling trees, equipment just wearing out. To survive all that, the grid needs an immune system, and it has to be one that can react way, way faster than any human ever could. And the stakes here are incredibly high. A single lightning strike, for example, carries an enormous amount of energy. If that fault isn't contained and isolated immediately, it can spread through the grid like a virus, tripping other lines, overwhelming other stations, and causing a cascading failure. And that's how you get a massive, widespread blackout. The grid's response to this is, frankly, a masterpiece of automated protection. All over the system, you have these things called protective relays. They're like the grid's nerve endings, constantly monitoring the flow of power. The second they sense the telltale signs of a fault, like a huge surge in current from a lightning strike, they instantly send a command to a nearby circuit breaker to trip open. This all happens in just a few milliseconds, literally faster than you can blink, to cut off and isolate the damaged section before the problem can spread. But what happens if that first line of defense fails? What if the relay or the breaker doesn't work?
Well, the whole system is designed with redundancy. There are always backup relays, and they're often located at a totally different station with their own separate power supply. So if the primary system fails for any reason, the backup protection kicks in to contain the fault. It's a defense-in-depth strategy.
So, we've figured out how to balance supply and demand, how to conquer distance, and how to protect the system from attack. But now we come to what might be the most mind-bending challenge of them all, a perfectly synchronized, continent-spanning dance.
This part is it's truly amazing. Every power plant, whether it's hydro, nuclear, or natural gas, has a massive generator inside, and that generator is spinning. And here's the crazy part. Every single one of those generators, we're talking thousands of them spread across an entire continent, has to spin in perfect lockstep with every other one. They are all physically and electrically connected in one great synchronized dance. And that rhythm has a very specific number, 50 cycles per second, or 50 hertz in many parts of the world. And this isn't just an average or a guideline, it is a precise frequency that has to be maintained across the entire network at all times. You can think of it as the very heartbeat of the grid.
Now let's go back to that lightning strike for a moment. When that protective system instantly cuts off a section of the grid, the generators that were feeding power to that section suddenly have nowhere for their energy to go. That sudden jolt of excess energy has to go somewhere, and what it does is it causes those generators to accelerate. They literally start to spin faster than the rest of the grid, threatening to break the rhythm of the dance and fall out of sync.
And if a generator falls too far out of sync, the system has no choice but to disconnect it to protect everything else, which could trigger a domino effect. But the grid has one last incredible trick. The sheer rotational mass of all the other thousands of generators connected to the grid acts like a massive inertial brake. It absorbs that sudden burst of energy and magnetically pulls that speeding generator back into the collective rhythm, restoring the harmony of the dance before a collapse can even begin.
So, we have balanced generation with demand, we've conquered immense distances, we've built a lightning-fast immune system, and we've choreographed a continent-wide dance, all of which brings this incredible, invisible journey right to your doorstep.
And that brings us right back to where we started, doesn't it? That simple, ordinary flick of a light switch. It feels so simple, so effortless. But as we've just seen, it's really the quiet culmination of an absolutely incredible, continent-spanning journey. One that involves solving a dozen impossible problems every single second of every single day.
Which, of course, leaves us with one final and pretty crucial question. This incredible machine was designed and built for a different era. But today, as we move to electrify everything, our cars, the way we heat our homes, our industries, the demands we're placing on it are changing dramatically. So the question is, can this invisible giant, this absolute master of the synchronized dance, adapt fast enough to keep up with the frantic new rhythm of our future?